What we are going to do now is use our circuit analysis techniques to develop a mathematical relationship that will allow us to determine the upper trigger limit and the lower trigger limit of an inverting Schmidt-trigger circuit. What we're going to do now is use circuit analysis techniques to develop a mathematical relationship that will allow us to determine the upper trigger limit and lower trigger limit of a non-inverting Schmidt-trigger op-amp circuit. We're going to do this by using the practical op-amp model. Okay? So if you recall, the practical op-amp model consists of an input resistance Rn that is between the non-inverting input terminal, which I'm labeling as V+, and the inverting input terminal, which I'm labeling as V-, which gives us a differential voltage of Vd over this input resistance. That's the input side of our practical model. The output side of our practical model consists of a voltage-controlled voltage source, where the voltage present across the terminals of this voltage-controlled voltage source is the open loop gain, AVOL, multiplied by our differential voltage, Vd. And then this is in series with our output resistance, Rout, and finally we have a ground connection that is our reference point for our circuit. So this is the practical op-amp model. Now we need to connect the other components that we have here in their appropriate places. So let's start by looking at the non-inverting input terminal. So the non-inverting input terminal is connected to one leg of a 1 kilo ohm resistor. So I'm going to draw my 1 kilo ohm resistor. R1 is equal to 1 kilo ohm. And the other leg of this 1 kilo ohm resistor is connected to our voltage source Vn. Vn is between that leg of the 1 kilo ohm resistor and our ground. So that seems like we should place it here, between our 1 kilo ohm resistor and ground. We also have this feedback path from the non-inverting input terminal to the output with a 3 kilo ohm resistor. So I'm going to draw that up here. So here is R2, our 3 kilo ohm resistor. We have a voltage source of 2 volts that is connected between the inverting input terminal and ground. So here's my reference voltage. Vref is equal to 2 volts. And lastly, I have an output voltage that is measured with respect to ground here. No load resistance or anything like that connected to it. Okay, so this is the practical op-amp model representation of this positive feedback op-amp circuit. Now what I'm going to do is I'm going to apply Kirchhoff's current law at the non-inverting terminal. So I'm going to take this current, and this current, add them together and set them equal to 0, because the law of conservation of charge must be maintained, even in an op-amp circuit. So let's start with our current directed to the left. That's going to be given by V plus minus Vn divided by R1. Then we're going to have our current directed down and to the right through our input resistor. V plus minus Vref divided by Rn. And lastly, we're going to have this current directed through our feedback loop. V plus minus V out divided by our resistor R2, and all of this is equal to 0. Now we're going to make an assumption here, okay? And this is a very important assumption to make. The assumption that we are making is that our input resistance Rn, which is typically on the order of mega ohms to tera ohms, is much, much larger than our resistor R1 and our resistor R2. So if Rn is much, much larger than R1 and R2, then the current flowing through our input resistance should be very, very small. V plus minus Vref divided by Rn will be approximately 0 amps. In practice, it will actually have a value, but it's on the order of picoamperes, which compared to the milliamps that we're seeing flowing elsewhere in the circuit is small enough to not be considered. Now, one consequence of this assumption is that V plus, our input voltage at the non-inverting terminal, is approximately equal to our reference voltage for our generic input voltage. So if we substitute in these relationships to our KCL equation, what we get is Vref divided by R1 minus Vn divided by R1. This middle term goes to 0, plus V plus divided by R2 minus V out divided by R2 is equal to 0. And now I'm going to algebraically rearrange this expression and solve for Vn. So Vn will be equal to R1 multiplied by our reference voltage Vref times 1 over R1 plus 1 over R2 minus V out over R2. This is the expression that is going to allow us to calculate our upper trigger limit and our lower trigger limit, because what we're trying to find is the input voltage that causes those transitions to happen, right? We know that our output is always going to be VCC plus or VCC minus. We're trying to now find the input voltages that causes the transition between those two states. So let's look at our upper trigger limit first. For our upper trigger limit, we are going to have Vn is equal to our 1 kilo ohm resistor multiplied by 2 volts times 1 over 1 kilo ohm plus 1 over 3 kilo ohms minus something, and we're going to talk about that in a moment, divided by 3 kilo ohms. The something that I have omitted here is the output voltage that we need to be using. This is where a lot of students struggle, okay? So since we are trying to determine the upper trigger limit, or the voltage that causes our output voltage to swing high, then the output voltage that we put here must be when it's at its low value, VCC minus, or in this case, negative 5 volts. If we use our calculator and solve this expression, we find that Vn is equal to 4.333 volts. So at a voltage of 4.333 volts, we should observe that our output voltage changes from VCC minus to VCC plus. For our lower trigger limit, we're going to use the exact same expression, but we're going to put VCC plus in instead of VCC minus. So we will have Vn is equal to 1 kiloohm times 2 volts, 1 divided by 1 kiloohm plus 1 over 3 kiloohms minus positive 5 volts, VCC plus, divided by 3 kiloohms, and we find that this is equal to 1 volt. So our output voltage changes from VCC plus down to VCC minus whenever our input voltage gets more or smaller than 1 volt. And I believe that these values match our simulation very well.